last thing we saw was what power of delta kills a certain sequence. Now let us try to figure out, given a diagonal, what sequence represents that diagonal. So example, suppose hn n is equal to 0 to infinity has its diagonal as 0, 0, 0, has diagonal 0, 0, 0, dot, dot, dot. Find hn. Find hn. Solution? Well, let's look at the difference table. The difference table looks like, well, my diagonal is 0, 0, 0, 0, 0, 0, right? I don't know what this is. I don't know what this is. I don't know what this is. And everything else I don't know, right? So maybe I'll just write all of these as stars rather than question marks. Star, 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 dot, 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 star, 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 dot, 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 star, dot, dot, dot. Okay, let us see what happens now. Because these two are 0, this term is forced to be 0, right? Because and this is my h0, this is my h0, which is equal to c0. This is c1. c0 plus c1 is equal to h1 because the h1 is difference between these two. So I get this is equal to 0. Well, by same logic, this is equal to 0. Well, since these two are 0, this is equal to 0. Similarly, since these two are 0, I get this is equal to 0. So this is equal to 0. Similarly, this is equal to 0. This is equal to 0. 0, 0, 0, 0, 0. And every single term is equal to 0, right? Therefore, my h of n is equal to 0. Right? And this has a very important consequence, corollary, that a sequence is uniquely determined by its diagonal. Sequence hn is uniquely determined by its diagonal sequence, right? And the proof is really easy. Proof. Suppose hn and gn, maybe, and gn n is equal to 0 to infinity, n is equal to 0 to infinity. Suppose they have the same diagonal sequence. Have the same diagonal sequence, right? We want to show that hn is equal to g1 and gn want to show hn is equal to gn for every n. Well, look at the sequence. The sequence hn minus gn. We have seen that this is going to have the difference quotient as 0 because difference quotient of Hn minus Gn is equal to difference quotient of Hn minus different quotients of Gn. And from my previous calculation, I can show that the diagonal depends only on the difference quotient or the difference diagram, right? From the so this has diagonal sequence 0, 0, 0, dot, 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 and therefore Hn minus Gn is equal to 0, since that is the only sequence that has any sequence that has diagonal sequence 0, 0, 0, 0, we have shown that that is equal to 0, and therefore Hn is equal to Gn for every n greater than or equal to 0. Okay, great. Example, find the sequence Hn whose Hn is equal to 0 to infinity, whose diagonal sequence is, let's say, 1, 3, 5, 2, 0, 0, 0, right? So, solution. Let us look at the sequence 1, 3, 5, 2, 0, 0, 0, dot, 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 is equal to 1 times 1, 0, 0, 0, dot, 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 plus 3 times 0, 1, 0, 0, dot, 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 plus 5 times 0, 0, 1, 0, dot, 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 plus 2 times 0, 0, 0, 2, dot, dot, 0, dot, dot, dot. And I know that the sequence that has the only sequence from my previous term that has the diagonal sequence 1, 0, 0, 0, 0 is h of 0, n choose 0. Let me write in. This is the diagonal sequence of n choose 0. This is diagonal sequence of n choose 1, n choose 2, n choose 3. And therefore, Hn is equal to 1 times n choose 0, plus 3 times n choose 1, plus 5 times n choose 3, plus 2 times n choose 4. Okay? Oh, sorry. My bad. That should have been... This should be 2 and 3. Not 3 and 4. Okay? So, we get a theorem. Given real numbers, C0, C1, dot, 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 CP, let Hn be, let Hn, n is equal to 0 to infinity, denote the sequence with diagonal sequence, denote the sequence with diagonal sequence C0, C1, C2, dot, 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 CP, and then zeros. Okay, then we can show that Hn is equal to C0 times n choose 0 plus C1 plus C1 times n choose 1 plus C2 times n choose 2 plus dot 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 plus Cp times n choose p. And the proof is basically what we did before. The corollary told me that, sequence is unique. So corollary plus the previous theorem, which told me that, sorry, that was a lemma. So lemma from previous part. Together, they say that, this is how I construct this sequence. Okay. Now, let us look at another important theorem. Given a sequence Hn, Hn, well, let me call it H is equal to Hn. Assume that it is killed by some power of delta. Assume there exists a p greater than 0, greater than or equal to 0, such that delta to the p plus 1 of H is equal to 0. Okay? We can say then there exists a polynomial f of x of degree smaller than or equal to p, such that Hn is equal to Fn, right? So we saw in lemma for every n is equal to 0, 1, 2, dot, dot, dot. So just to comment, in the lemma we saw that if Hn was a polynomial of degree p, which is equal to Fn, then delta to the p plus 1 annihilated it. It sent it to 0, right? Now we are trying to say exactly the other way around. If it is being indeed annihilated by delta to the p plus 1, we want to say it is equal to a polynomial. Proof. Let Cn n is equal to 0 to infinity denote the diagonal sequence for f. Denote the diagonal sequence for H. Okay. Then observe that C of n is equal to 0 if n is greater than or equal to p plus 1, right? Because what is going to happen? My delta to the p plus 1 kills it, right? So it should be the delta to the p plus 1 throw should be identically 0. If delta to the p plus 1 throw is identically 0, then everything below it, including the diagonal sequence, is going to be consistently 0, right? Therefore, this is 0. Then, by previous theorem, Hn is equal to, well, C0 n choose 0 plus C1 n choose 1 plus dot 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 Cp and choose p, right? Then define f of x is equal to C0 and C0 x choose 0 plus C1 x choose 1 plus dot 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 CP x choose P. Okay. Then f of x has degree. Then f of x has degree P if CP is not equal to 0. Right? And if it is P minus 1, it is going to be and less than or equal to and degree smaller than or equal to P as P minus 1 if, well, strictly smaller than P, let me say this. Degree is strictly smaller than P if CP is equal to 0, right? In neither case is it going to have degree more than P, because we know x choose 0 is a degree 0 polynomial, which is just 1, since x choose 0 is 1. X choose 1 is just x, that's a degree 1 polynomial. X choose P is a degree P polynomial. We have seen this before. Right? And therefore, Hn is equal to f of n for a degree P polynomial, for a degree at most P polynomial as required. Okay, I will stop this example. Actually, let me just finish the sequence. Okay, let me finish this part. This is going to be slightly longer. Find a formula for example. Find a formula for let's go for the sequence for Hn. 1 to the 4 plus 2 to the 4 plus 3 to the 4 plus 4 to the 4 plus dot 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 plus n to the power 4, right? You know the formula for summation 1 to n. You might know the formula for n squared and n cubed. Let us try to find the formula for n to the 4. Solution. Consider the sequence. Consider the sequence n to the 4. N is equal to 0 to infinity. Okay. And let us look at its diagonal sequence. Find the diagonal sequence. Diagonal sequence. It is going to be 0, 1, 0 to the 4, 1 to the 4, 2 to the 4, 3 to the 4, 4 to the 4, 5 to the 4, 6 to the 4, dot dot dot. And this is going to look like, let me write down the values in red as I usually do. 0, 1, 16, 81, 16 squared, 256, 625, and 1296, 1296. Okay, let us look at the different sequence. 1, 15, 65, 175, 369, and this is 671, if I'm not wrong. Okay, next, 14, 50, 110, 194. Yep. And this is 302. Okay. Next. This was 50, not 56. 50. 36, 60, 84, 8, so 208. No, 108. 108. Great. Let us look at here. 24, 24, 24, and then in my sixth row, I am going to get 0, 0, 0, 0. And therefore, my sequence is diagonal sequence. Diagonal sequence is 0, 1, 14, 36, 24, 0, 0, 0, dot, dot, dot. Right? And therefore, I have that n to the 4 is equal to n choose 1 plus 14 times n choose 2 plus 36 times n choose 3 plus 24 times n choose 4, and then it's going to be zeros. Great, I have found a formula for n to the power 4, but that is not the entire question. The question is asking for 1 to the 4 plus 2 to the 4 plus 3 to the 4, all these things, right? Recall, 0 to the k plus 1 to the k plus 2 to the k plus dot 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 plus n to the k, sorry, n choose k, 0 choose k, 1 choose k, 2 choose k, all the way up to n choose k. We have seen that this was n plus 1 choose k plus 1, right? We saw this one before. And hence, therefore, 1 to the 4 plus 2 to the 4 plus 3 to the 4 plus dot 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 n to the 4 is equal to, all of these are going to get summed up, n plus 1 choose 1 plus 1, which is 2, plus 14 times n plus 1 times 2 plus 1, which is 3, plus 36 times n plus 1 times choose 4, plus 24 times n plus 1 choose 5. Okay? And so, example, if I want a polynomial sequence, given a polynomial sequence f, given a polynomial, not sequence, given a polynomial f of x of degree p, find formula for f0 plus f1 plus f2 plus dot 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 plus fn. Okay, I want to do this. Solution. Consider the sequence. Consider the sequence f of n, n is equal to 0 to infinity. Let Cn denote the diagonal sequence. Let Cn, n is equal to 0 to infinity, denote its diagonal sequence. Denote its diagonal sequence. Well, again, No, then Cn is equal to 0 for every n greater than p, right? Therefore, Fn, f of n is equal to, from what we have seen before, if this is the diagonal sequence Cn, then Fn is going to be n choose 0 plus n plus C1 from C1 n choose 1 plus dot 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 Cn, whoops, Cp n choose p, right? And therefore F0 plus F1 plus dot 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 plus Fn is equal to, well, let me write down the equal to here, is equal to C0 times n choose 1 by exactly the same logic as before. Oops, not n choose 1, n plus 1 choose 1 plus C1 times n plus 1 choose 2 plus C2 times n plus n plus 1 choose 3 plus dot 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 Cp times n plus 1 choose p plus 1. Okay, and that will stop this video. I will cover on the exam only till this part. I will publish notes for Stirling numbers also, but I won't ask them on the exam. They are slightly annoying, and I don't want to overburden you before the exam. Okay, so you only need to cover this part till the exam, even though the homework will have Stirling numbers. Okay.